Modern concrete cracks within years. Bridges crumble. Buildings deteriorate. Roman concrete, mixed 2,000 years ago, grows stronger with time. The Pantheon's dome, cast in 126 CE, remains the world's largest unreinforced concrete dome, uncracked and load-bearing after 19 centuries. Medieval masons inherited this knowledge, creating mortar that self-repairs, that strengthens underwater, that outlasts the stones it binds. This is the story of a building material so sophisticated that modern engineers are only now discovering why it works and why everything we've built in the last century is designed to fail. Chapter 1. The crack that spreads like disease. Drive across any highway bridge built after 1950. Look at the concrete surface. See the spiderweb of cracks spreading across support columns. Those cracks widen every winter water seeps in, freezes, expands, forcing the cracks wider. Salt from de-icing accelerates corrosion of internal steel reinforcement. The corroding steel expands, creating pressure that spawns new cracks. The cycle accelerates until structural failure becomes inevitable. The American Society of Civil Engineers estimates that 42% of American bridges are over 50 years old, and 7.5% are structurally deficient. The deficiency is primarily concrete deterioration. The fundamental building material of modern civilization is failing catastrophically across millions of structures worldwide. Bridge reconstruction costs exceed $125 billion in the United States alone. That's not building new infrastructure. That's replacing infrastructure that's barely old enough to qualify as heritage. A bridge built in 1960 is being demolished in 2024 because its concrete has failed. Meanwhile, the Pont du Gard aqueduct in southern France, built by Romans in 50 CE using concrete and stone, still stands. No steel reinforcement, no modern admixtures. Just lime, volcanic ash, aggregate, and water, mixed according to techniques Romans learned from earlier civilizations. The aqueduct carried water for 500 years, then served as a bridge for another 1,500 years. It's still structurally sound today, 2,000 years after construction. Modern engineers examining the Pont du Gard discovered something disturbing. The Roman concrete is stronger now than when originally built. Mechanical testing shows compressive strength has increased over 2 millennia. The material has improved with age. Modern concrete reaches peak strength at 28 days, then begins a slow decline. By 50 to 100 years, significant degradation is typical. Roman concrete strengthens for centuries. We've replaced a building material that improves over time with one that deteriorates from the moment it's cast. Chapter 2. The volcanic secret. Roman concrete begins with a specific ingredient, pozzolana, volcanic ash from regions near Mount Vesuvius, and throughout the Roman Empire. This ash isn't ordinary. It contains specific minerals formed by volcanic processes that create unique chemical properties. When mixed with lime and water, pozzolana undergoes pozzolanic reaction, a chemical process where silica and alumina in the ash react with calcium hydroxide to form calcium silicate hydrates and calcium aluminate hydrates. These compounds are extraordinarily stable, water-resistant, and strong. Medieval masons, inheriting Roman knowledge, sought similar materials. In regions without volcanic ash, they used crushed brick or tile-fired clay that had undergone thermal transformation, creating similar reactive silicates. In other areas, they used finely ground blast furnace slag or certain types of clay. Each material worked through the same principle. Reactive silica combining with lime to form hydraulic compounds that set even underwater. The key is particle size and reactivity. Volcanic ash particles are microscopically small, typically 1 to 50 micrometers with highly irregular surfaces, providing enormous surface area for chemical reaction. When mixed with lime, the ash particles become nucleation sites for crystal growth. Calcium silicate hydrates grow from each particle, creating interconnected network throughout the mortar matrix. This network is the source of strength. Modern concrete uses Portland cement, developed in 1824 by heating limestone and clay to 1,000, 450 degrees Celsius, then grinding the resulting clinker into powder. Portland cement is reactive, consistent, and fast-setting. It's also fundamentally different from Roman lime pozzolan mortar. Portland cement forms calcium silicate hydrate crystals through cement hydration, a rapid chemical reaction that's essentially complete within weeks. The resulting structure is strong, but static. Roman pozzolanic mortar forms crystals through slower reaction. The process continues for years, even centuries. As long as moisture and unreacted material remain, the structure evolves, densifies, and strengthens indefinitely. The University of California, Berkeley, analyzed Roman concrete samples from various structures using scanning electron microscopy to examine crystal structure at nanoscale. They found evidence of continuing crystal growth in 2,000-year-old samples. The concrete was still curing, still developing new calcium silicate hydrate connections, still getting stronger. The material was alive in a chemical sense, continuously improving its structure. Chapter 3. The water that builds stone. Roman concrete does something modern concrete cannot. It thrives in seawater. The Romans built harbors, breakwaters, and marine structures using concrete that set underwater and strengthened through contact with seawater. These structures remain functional 2,000 years later. Modern concrete in seawater deteriorates rapidly, typically 50 to 100 years before requiring major repair or replacement. Salt water penetrates concrete, corroding steel reinforcement and triggering chemical reactions that weaken the cement matrix. Offshore structures require continuous maintenance against inevitable degradation. The difference is chemistry. Seawater contains dissolved minerals, sodium, magnesium, chloride, that react destructively with Portland cement. But these same minerals react constructively with Roman pozzolanic concrete. Researchers at the University of Utah discovered the mechanism by analyzing Roman harbor concrete from Portus Cosanus, a harbor near Rome. The concrete was submerged in seawater for 2,000 years. Instead of deteriorating, it had grown denser and stronger. Microscopic analysis revealed why. The volcanic ash contained a mineral called aluminum tobamorite, which is stable in seawater. More remarkably, seawater reactions had created additional aluminum tobamorite crystals throughout the concrete, filling microscopic voids and strengthening the structure. The seawater wasn't corroding the concrete, it was feeding crystal growth that reinforced the material. The process is self-sustaining. Seawater seeps into microscopic cracks, bringing dissolved minerals. These minerals react with unreacted volcanic ash particles, forming new crystals that fill the cracks. The concrete self-heals, closing gaps before they become structural problems. Medieval masons working on coastal fortifications and harbor structures understood this empirically. They knew certain mortar formulations performed better in marine environments. They couldn't explain aluminum tobamorite formation, but they observed that structures built with volcanic ash mortar lasted indefinitely in seawater while other mortars failed. They encoded this knowledge in practice. For marine construction, use pozzolanic mortar. The rule preserved the technique, even as understanding of underlying chemistry was lost. Chapter 4. The lime that breathes. Medieval mortar was made from lime calcium oxide, produced by heating limestone to 900 to 1,000 degrees Celsius in kilns, then slaking with water to produce calcium hydroxide. This lime mortar has properties Portland cement lacks. It's flexible, vapor-permeable, and chemically compatible with historic stone. Flexibility matters enormously. Buildings move, foundation settling, thermal expansion, wind loading, and seismic activity all create stresses. Rigid mortar cracks under these stresses. Flexible lime mortar deforms slightly, absorbing movement without cracking. The flexibility comes from lime mortar's structure. It's not a solid mass, but a matrix of calcium carbonate crystals bound in calcium hydroxide paste. The paste provides cushioning, allowing slight movement while the crystals provide strength. As lime mortar ages, It undergoes carbonation. Calcium hydroxide reacts with atmospheric carbon dioxide, slowly converting to calcium carbonate limestone. The mortar is literally turning back into stone, but doing so gradually over decades or centuries. This slow curing allows the mortar to accommodate building movement during the vulnerable early period, then gradually strengthen as the structure stabilizes. Portland cement mortar cures in weeks, becoming rigid before the building has fully settled. Any subsequent movement creates cracks. Vapor permeability is equally critical. Stone contains moisture, water absorbed from rain, groundwater wicking through foundations, humidity condensing in pores. This moisture must escape, or it causes deterioration. Lime mortar is porous enough to allow vapor transmission. Moisture moves through the mortar joints, evaporating harmlessly. Portland cement is much less permeable. Moisture becomes trapped, causing stone to deteriorate through freeze-thaw cycles and salt crystallization. Buildings pointed with cement mortar show characteristic damage. The stone faces spalling and crumbling, while cement joints remain intact. The hard, impermeable mortar has destroyed the softer, more valuable stone. Buildings pointed with lime mortar show the opposite pattern. Mortar erodes slowly, while stone remains intact. The mortar sacrifices itself to protect the stone. This is appropriate. Mortar is replaceable. Stones are not. Medieval masons understood this hierarchy. Use softer, more permeable mortar to protect harder, more valuable stone. Modern masons, taught that harder is always better, use Portland cement that destroys historic masonry. Chapter 5. The aggregate that matters. Mortar is only part of concrete. The other components are aggregate, sand, gravel, and crushed stone that make up 60–80% of concrete's volume. Romans and medieval builders were obsessive about aggregate selection, specifying sources, sizes, and preparation methods with precision that seems excessive until you understand the consequences. Aggregate does more than fill space, it provides structural skeleton. The mortar binds aggregate particles, but the particles themselves carry most load. Aggregate quality directly affects concrete strength, durability, and longevity. Romans used specific volcanic gravels, pumice, scoria, and basalt fragments that had complementary properties to their pozzolanic mortar. The volcanic stones had similar thermal expansion coefficients to the mortar, preventing stress from temperature changes. They were porous, allowing the mortar to penetrate and create mechanical interlocking. And they were chemically compatible, avoiding reactions that would weaken the interface. Medieval builders, lacking volcanic aggregate in many regions, developed sophisticated classification systems. They distinguished river gravel from crushed stone, sharp-edged from rounded particles, dense from porous materials. They knew that rounded river gravel creates weak concrete because particles don't interlock, the mortar must carry all load. Crushed stone with angular fragments creates strong concrete through mechanical interlocking. The Technical University of Munich analyzed medieval mortars from various structures, cataloging aggregate types and their distribution. They found that masons selected aggregate based on application. Fine, sharp sand for thin joints in precision stonework. Coarse, angular gravel for thick concrete pours in foundations. Lightweight pumice for vaults requiring reduced weight. Each aggregate was optimized for specific structural requirements. Modern concrete typically uses whatever aggregate is locally cheapest, often river gravel or crushed limestone, without consideration for particle shape, size distribution, or chemical compatibility. The variability contributes to unpredictable concrete performance. Two structures built with identical Portland cement, but different aggregate, can have dramatically different durability. Chapter 6. The mix that balances forever. Medieval mortar recipes specified proportions with remarkable precision. 3 parts sand to 1 part lime for general masonry. 2 parts sand to 1 part lime for finer work. 1 part sand to 1 part lime to 1 part pozzolana for hydraulic mortar setting underwater. These ratios weren't arbitrary, they represented centuries of empirical optimization. Too much lime creates mortar, that's expensive, shrinks excessively during curing, and cracks. Too little lime creates weak mortar that crumbles. The 3-to-1 ratio for general masonry represents optimal balance between strength, economy, and workability. But the ratios varied by application. The mortar binding large foundation stones could be coarse and economical 4-to-1 or even 5-to-1 sand to lime. The mortar for thin joints in ashlar masonry needed to be fine and strong 2-to-1 or richer. The masons adjusted proportions based on materials, climate, structural requirements, and aesthetic considerations. Modern concrete uses standardized mixes, particular cement, aggregate, water ratios, designed to achieve specific compressive strengths. The standardization enables quality control but eliminates optimization for specific conditions. A concrete mix, designed for California's dry climate, performs poorly in Maine's freeze-thaw cycles. A mix optimized for rapid construction may sacrifice long-term durability. Medieval variability, different mixes for different purposes, created appropriate performance across diverse conditions. The Institut Royal du Patrimoine Artistique in Belgium analyzed mortars from medieval buildings across Europe, documenting hundreds of distinct formulations. They found systematic regional variations. Mediterranean mortars used more pozzolan. Nordic mortars used richer lime content. Coastal mortars incorporated crushed shell. Each adaptation addressed local climate, available materials, and structural requirements. The diversity was sophisticated engineering response to variable conditions. Modern standardization is engineering convenience that ignores local optimization. Chapter 7. The craft that reads the weather. Medieval masons didn't mix mortar by measuring, they mixed by feel, adjusting water content based on temperature, humidity, and sand moisture. This seems imprecise, but it achieved better results than modern volumetric batching. Mortar workability depends on water content, but the correct amount varies with conditions. Hot, dry weather requires more water. The mortar dries rapidly and needs fluidity to remain workable. Cold, humid weather requires less water. Excess moisture slows curing and risks frost damage. Sand moisture complicates everything. Wet sand contains water that must be accounted for, or the mortar becomes too fluid. Medieval masons learned to judge sand moisture by touch and appearance, adjusting mix water accordingly. They knew correct consistency by how mortar behaved on the trowel, how it spread on stone, how quickly it stiffened. This tacit knowledge, developed through years of practice, produced consistently good mortar across varying conditions. Modern concrete batching uses fixed water-cement ratios, typically 0.4 to 0.6 by weight. This ensures consistency, but ignores environmental variables. Concrete mixed on hot, dry days dries too quickly, compromising hydration and strength. Concrete mixed in humid conditions may be too fluid, leading to segregation and weak structure. Quality control attempts to address this through admixtures, chemicals that modify setting time, fluidity, or other properties. But admixtures are compensating for inflexible base formulations. Medieval masons achieved appropriate performance through adjustment, not addition. The knowledge was experiential. Every mason learned by mixing countless batches, observing how different proportions behaved in different conditions, developing intuition that guided adjustments. This cannot be taught from books or specifications. It requires practice under supervision of experienced craftsmen. As traditional masonry declines, this knowledge is vanishing. Young masons learn to follow mixed designs, not to judge and adjust. The skill of reading materials and conditions is being lost. Chapter 8. The structure that stands without steel. The Pantheon in Rome, completed 126 CE, features a concrete dome spanning 43.3 meters. No steel reinforcement, no tension members, just unreinforced concrete, supporting its own weight for 1,900 years without cracking. Modern structural engineering claims this is impossible. Unreinforced concrete has poor tensile strength, It fails under tension before reaching its compressive capacity. Large concrete structures require steel reinforcement to carry tensile loads, yet the Pantheon contradicts this understanding. The secret is structure and material working together. The dome's geometry, a perfect hemisphere, converts all loads into compression. There are no significant tensile forces requiring reinforcement. The concrete itself varies throughout the structure: dense, heavy aggregate at the base, transitioning to lightweight pumice at the crown, reducing weight where structure is most stressed. The concrete mix also varies: richer, stronger mortar at the base, leaner mix at the crown. Medieval cathedral builders inherited these principles. Gothic vaults spanning 20 to 30 meters were built with unreinforced stone and mortar, using geometry to eliminate tension. The pointed arch, ribbed vault, and flying buttress all served one purpose: directing forces into compression paths through stone. The structures remain standing because the design never asks materials to do what they cannot. Modern structural engineering takes the opposite approach: use high-strength materials to resist forces in any direction. Concrete beams reinforced with steel can span great distances while carrying tensile loads. This works excellently until the steel corrodes. Then the structure fails catastrophically. Medieval structures, designed to work without reinforcement, cannot fail through reinforcement corrosion because they have no reinforcement. They fail only if overloaded beyond design capacity, or if foundation settling creates loads the structure cannot accommodate. With reasonable maintenance, they last indefinitely. The University of Bologna's Department of Civil Engineering conducted structural analysis of medieval vaulted structures, using finite element modeling to calculate stress distributions. Their findings confirmed what medieval builders knew empirically. Properly designed, unreinforced masonry develops only compressive stresses. No tension means no need for reinforcement. The structures are optimized for their materials' properties. Modern reinforced concrete is optimized for structural efficiency, accepting material vulnerability in exchange for lighter, more economical construction. This trade-off works for structures with 50 to 100-year design lives. For permanent structures, medieval unreinforced masonry proves superior. Chapter 9. The repair that continues forever. Medieval buildings weren't maintained, they were continuously repaired. Mortar, eroded by weather, was repointed every 50 to 100 years. Stone, damaged by weathering, was replaced. Structural movement was accommodated through incremental adjustment. The buildings evolved through constant intervention, remaining functional despite never being preserved, unchanged. This maintenance philosophy differs fundamentally from modern conservation. We attempt to stabilize structures in their current state, arresting decay through interventions intended to last decades. Medieval maintenance accepted ongoing decay as normal, addressing it through regular small repairs rather than occasional large interventions. The practical advantage is enormous. Small repairs are affordable. Any competent mason can repoint mortar joints or replace a damaged stone. Large interventions require specialized conservators, engineering analysis, and substantial funding. Buildings awaiting proper conservation deteriorate while waiting for resources that may never arrive. Buildings maintained through regular small repairs remain functional indefinitely. The Chapel of King's College, Cambridge, built 1446 to 1515, has been continuously repaired throughout its 500-year existence. The fabric has been maintained through countless small interventions: repointing mortar, replacing weathered stones, adjusting drainage, cleaning. No comprehensive restoration has ever occurred, just ongoing repair. The building remains structurally sound and beautiful because it's never been allowed to deteriorate to the point requiring major intervention. Compare this to many 20th-century concrete structures, which received minimal maintenance until deterioration became crisis. Now they require expensive reconstruction or demolition. The maintenance philosophy, defer spending until failure is imminent, has proven catastrophically expensive. Medieval approach, spend consistently on preventive maintenance, proves far more economical across building lifetimes. But our economic and institutional systems don't accommodate continuous maintenance. Building budgets fund construction, not upkeep. Organizations defer maintenance to minimize annual costs, even though deferred maintenance increases lifetime costs exponentially. We've created incentive structures that ensure building failure. Chapter 10. The Chemistry Rediscovered. In 2017, a team led by MIT professor Adma Masic analyzed Roman concrete samples using advanced spectroscopy and microscopy. They discovered something that had been overlooked. The concrete contained small, white inclusions throughout fragments of lime that hadn't fully reacted during mixing. Previous researchers had dismissed these as evidence of poor quality control in completely mixed lime. Masic's team realized they were seeing evidence of hot mixing, adding quicklime, calcium oxide, directly to the mix, rather than pre-slaking it to form lime putty. When quicklime contacts water in the concrete mix, it reacts violently, generating heat. This heat accelerates pozzolanic reactions and creates lime-clasts small, highly reactive calcium hydroxide nodules throughout the concrete. These lime-clasts are the key to self-healing. When cracks form in Roman concrete, water seeping through the crack dissolves lime from the clasts. This dissolved lime migrates to the crack surfaces, where it reacts with carbon dioxide to form calcium carbonate, sealing the crack. The concrete heals itself automatically, using its own chemical reserves. Modern concrete has no such mechanism. Portland cement provides no reservoir of reactive material for self-repair. Cracks propagate until they cause structural failure. The research team tested hot mixing in modern concrete formulations, creating samples with deliberate lime clasts. They cracked the samples, then exposed them to water. Within 14 days, the cracks had sealed themselves through calcite formation. The healed cracks were as strong as uncracked concrete. They'd rediscovered a 2,000-year-old technique that makes concrete self-repairing. The implications are staggering. Infrastructure that heals its own cracks would last far longer with less maintenance. The technology exists. It's been working in Roman concrete for 2 millennia. Implementing it requires only returning to mixing methods we abandoned in pursuit of faster, more standardized production. But hot mixing creates challenges for modern construction. The heat generation complicates quality control. The reactive lime clasts can cause expansion if not properly managed. The technique requires skill and attention, incompatible with high-volume production. So despite knowing how to make self-healing concrete, we continue building with concrete that cannot repair itself. Chapter 11. The Economics of Deterioration. The construction industry is optimized for building, not maintaining. Contractors profit from new construction, not from keeping old buildings functional. Material suppliers sell cement, not durability. The economic incentives point toward construction, not preservation. This creates perverse outcomes. A bridge that lasts 50 years generates reconstruction revenue every half-century. A bridge that lasts 500 years generates revenue once. From industry perspective, durability is lost opportunity. This isn't conspiracy, it's economic logic. Companies maximize profit by maximizing sales. Durable products reduce sales. Therefore, companies avoid creating durable products when possible. This explains why Roman concrete techniques haven't been widely adopted despite clear superiority. Implementing them would extend infrastructure lifespan by factors of 5 to 10, devastating the reconstruction market. The construction industry would shrink dramatically. From societal perspective, this is desirable, durable infrastructure reduces long-term costs. From industry perspective, its catastrophic reduced sales mean reduced profits. The industry has enormous political influence, shaping building codes, infrastructure planning, and funding priorities. Codes that mandate Portland cement benefit cement manufacturers. Standards that require frequent bridge inspection and reconstruction benefit construction companies. The regulatory framework serves industry interests, not longevity. Medieval construction operated under different economics. Master masons were paid for their skill, not for material volume. Their reputation depended on structures lasting. There was no reconstruction industry profiting from failure, just craftsmen whose status came from buildings that endured. The incentive structure rewarded durability. Until we change economic incentives, we'll continue building infrastructure designed to fail. We know how to build structures lasting millennia. We choose not to because failure is more profitable than permanence. Chapter 12. The Mason Who Remembers. In Somerset, England, a stonemason named James Giles specializes in lime mortar repair, using traditional techniques. He's 58, learned the craft from his father, who learned from his grandfather, who worked on Victorian restorations of medieval buildings in the 1880 seconds. The knowledge chain is tangible techniques passed through direct instruction across 140 years. James is repairing a 15th century parish church. The previous repair, done in 1970 with Portland cement, has failed catastrophically. The cement mortar, harder than the stone, has caused the stones to deteriorate. Faces have spalled off. Salt has crystallized in pores. The damage is severe. James is removing the cement carefully to avoid damaging stone further and replacing it with lime mortar matching the original. He mixes the mortar on site. 3 parts sand to 1 part lime, plus a handful of goat hair for reinforcement. The hair prevents cracking as mortar dries. Medieval masons used horsehair, cow hair, whatever was available. The principle remains organic fiber provides micro-reinforcement that synthetic fibers cannot match. He points the joints slowly, pressing mortar firmly into voids, ensuring complete filling. The work takes weeks. Lime mortar must be applied in thin layers, allowing each layer to carbonate before adding the next. Rush the process, and the mortar remains weak. Respect the material's chemistry, and it performs beautifully. James explains the economics. His repair costs £12,000 versus £8,000 for cement repointing, but his work will last 80 to 100 years. The cement repointing lasted 30 years before failing and caused expensive stone damage requiring additional repair. Total cost over 100 years. Cement approach requires 3 repointing cycles, plus stone repair, totaling £35,000 plus. Lime approach requires 1 repointing, totaling £12,000. The expensive traditional method is far cheaper across realistic timeframes, but parish councils see initial cost, not life cycle cost. They often choose cement because it's cheaper now, even though it's more expensive later and damages irreplaceable heritage. James has trained 2 apprentices in 30 years. 1 is still practicing. The ratio is unsustainable practitioners retiring faster than apprentices learning. In 20 years, there may not be enough skilled lime masons to maintain Britain's medieval building stock. The knowledge will exist in books, but the craft, the tactile judgment, the experiential understanding will be gone. Chapter 13. The standard that prohibits excellence. Modern building codes, developed for Portland cement construction, often prohibit or complicate use of lime mortar. Codes specify minimum compressive strength that lime mortar cannot achieve. They require curing times incompatible with lime's slow carbonation. They mandate testing procedures designed for Portland cement that don't apply to lime. This regulatory framework makes traditional construction difficult or impossible, even when it's technically superior. Codes are developed by committees, including industry representatives. Portland cement manufacturers have a seat at the table. Lime producers don't, the market is too small. So codes encode practices that favor cement, disadvantaging or excluding alternatives. Getting code approval for lime mortar requires variance, demonstrating that the non-standard approach provides equivalent performance. This requires engineering analysis, testing, and documentation that small projects cannot afford. So lime mortar gets used only in heritage conservation, where its necessity is recognized. New construction uses cement by default. Some jurisdictions are reforming. Historic England now recommends lime mortar for any building constructed before 1919, regardless of heritage designation. They've developed guidance documents explaining appropriate mortar selection and application. This helps, but it's guidance, not code. Building owners can ignore it without consequence. Scotland has gone further, incorporating traditional materials and techniques into mainstream building standards. Scottish building regulations explicitly accommodate lime mortar, specifying appropriate applications and performance criteria. This makes traditional construction legally straightforward. The result: Scotland has healthier lime mortar industry and better maintained historic buildings than England. Regulatory framework shapes industry practice. Codes that accommodate traditional techniques enable their survival. Codes that ignore or prohibit them ensure their extinction. Most jurisdictions have codes that assume Portland cement is the only mortar. Traditional techniques survive despite the regulations, not because of them. Chapter 14. The research that changes everything. Contemporary materials science is rediscovering medieval mortar principles and validating their superiority. Research programs at major universities are analyzing historic mortars, testing traditional techniques, and developing new materials inspired by ancient approaches. The European Union funded a major research initiative, Rocaire, Roman cement, and concrete. Over 5 years, teams from 15 universities analyzed Roman concrete from structures across the former empire. They documented composition, manufacturing techniques, and durability mechanisms. The findings are being compiled into guidelines for creating modern materials using Roman principles. Similar research in Japan is studying traditional Japanese lime mortars, which used crushed shell instead of limestone, creating different chemistry with excellent performance. In India, researchers are analyzing traditional Surkey mortars, made with lime and finely ground brick, which set hydraulically like Roman pozzolanic concrete. The traditional knowledge exists globally, in dozens of cultures, largely undocumented by modern science. Commercial applications are emerging. Several companies now produce Roman cement, modern formulations using volcanic ash or similar pozzolans with lime, creating slow-curing, durable mortars for specialty applications. The market is tiny compared to Portland cement, but it's growing. Architects specifying Roman cement for high-profile projects demonstrate its viability. Engineers using it for marine structures prove its performance. Each successful application challenges the assumption that Portland cement is the only option. But mainstream adoption faces barriers. Roman cement is slower curing times of months versus weeks. Its more expensive, specialized materials and skilled labor cost more than commodity cement. Its unfamiliar engineers, contractors, and code officials don't understand it. These barriers are surmountable, but require institutional change. Education systems must teach traditional techniques. Professional organizations must develop standards and best practices. Codes must accommodate alternatives to Portland cement. None of this happens quickly. Knowledge institutions move slowly, and cement industry actively opposes changes threatening their market dominance. The research proving traditional mortar superiority is barely 15 years old. Translating research into widespread practice typically takes 30 to 50 years. We're in early stages of rediscovery. The question is whether the knowledge resurrection happens fast enough to prevent complete loss of traditional craft skills. Chapter 15. The mortar that waits. You cannot buy Roman concrete at hardware stores, but you can make lime mortar with materials available from masonry suppliers. Hydrated lime, sand, and optional, pozzolan, for hydraulic properties. The technique is documented in dozens of books and online resources. The equipment is basic mixing container, trowel, water. Total cost for small batches, under $50. The knowledge is accessible. The barriers aren't technical, they're cultural and regulatory. Using traditional mortar for permitted construction requires navigating codes written for modern materials. Convincing contractors to work with unfamiliar materials requires education and possibly higher costs. Accepting slower curing times requires patience, incompatible with construction schedules. For DIY applications, garden walls, personal projects, non-permitted work, traditional mortar is entirely feasible. For professional construction, barriers are substantial but not insurmountable. The advantage is permanence. Structures built with traditional lime mortar, using appropriate techniques, last centuries with minimal maintenance. Structures built with Portland cement require major intervention within decades. The choice is between initial convenience and long-term durability. Medieval masons chose durability. They built for posterity, creating structures serving descendants 10 generations removed. We build for the present, creating structures that will burden our children with demolition and reconstruction costs. The mortar that heals itself is still possible. The chemistry works. The techniques are documented. The materials are available. What's missing is cultural willingness to prioritize permanence over convenience, to value centuries over quarters, to build like our existence extends beyond our individual lifetimes. Roman concrete is waiting. Not in stores, in understanding. The knowledge that permanence is possible, that materials can improve with age, that infrastructure can serve civilizations rather than requiring reconstruction every generation. Medieval mortar is waiting. Not as historical curiosity, as viable technology. The principles that made it superior haven't changed. We changed, prioritizing speed and economy over durability and longevity. The question is whether we'll remember. Before the last masons who know how to mix it properly retire, and the knowledge becomes archaeological curiosity rather than living practice. The mortar knows its purpose. It's prepared to last millennia. We just have to be worthy of building with it.